Welcome back to the deep dive. Today we're jumping into a pretty critical data engineering rescue mission.
Yeah, that's a good way to put it.
Imagine you're running a small grocery chain, right? Healthy foods focus, you're doing great, expanding really fast.
Almost too fast for the back office, it sounds like.
Yeah,
Exactly. You're going from just 3 stores up to 10. But here's the catch. Your entire business history, like one whole year's worth of data, it's all stuck in this tangled web of Excel spreadsheets. The classic Excel spaghetti. I know it well. Sales, items, categories, promotions, everything critical is in there somewhere.
but it's a mess. Try to combine them and you hit all the usual problems.
Oh, yeah. Duplicated headers popping up everywhere, columns with numbers and text mixed together, dates formatted like 10 different ways, and my personal favorite, category naming drift. Ugh, don't remind me. Dairy milk alternatives versus alt milk dairy versus non-dairy milk. Good luck getting consistent reporting out of that.
Right, you just can't trust the insights. So, our focus today is nailing challenge 01. It's the absolute first step. We have to take this denormalized chaos
The spreadsheet nightmare.
and turn it into a clean, reliable Postgres database, properly structured, normalized, and ready for some basic prediction work. The mission, should we choose to accept it, involves 4 key things. First, figure out the underlying structure, reverse engineer a conceptual model,
Okay,
a blueprint.
exactly. Second, translate that blueprint into actual SQL database code, making sure it's normalized to what we call third normal form, or 3NF.
Got it. Third,
Reliably get the data in there. That means building an automated ETL pipeline extract, transform, load,
and finally,
produce something useful,
Huh.
a baseline predictive model, like, say, predicting daily sales for each store. We need to build the foundation and show it can support something practical right away.
okay, let's unpack that first part, the structure. Moving from flat spreadsheets where one row tries to do everything.
Yeah, telling you the product, the store, the vendor, the price, the quantity, all crammed together.
That just leads to so much repeated information. Redundancy.
And that redundancy isn't just messy, it's risky, especially when you're trying to grow. That's where 3NF comes in. Right. We need to eliminate what are called transitive dependencies.
Okay, break that down. Transitive dependencies.
Basically, it means everything in a specific table should depend only on that table's main identifier, its primary key, nothing else.
So like if the store manager's name depends on the store ID,
Right, and the store ID is maybe the primary key of a store table.
then the manager's name belongs in the store table, not repeated in every single sales transaction record for that store.
Exactly. It shouldn't be transiting through the sales table.
Now, why 3NF specifically? I mean, sometimes you hear about star schemas for faster reporting, maybe less strict normalization.
That's a fair question. It's a common debate. But for this initial foundational build, 3NF is kind of non-negotiable. It prioritizes data integrity above all else.
And integrity is key when you're adding 7 new stores.
Think about it. They need to update, say, the address for store 001. In a proper 3NF design, you change one row in the dim store table. Done.
Whereas in the old Excel world,
You'd potentially have to find and replace that address in thousands, maybe tens of thousands of individual sales rows. Huge potential for error. 3NF prevents those update anomalies. It gives you stability.
makes total sense. Integrity first, then optimize for speed later if needed. So the design involves breaking things down. We get these dimension tables.
Right. Dimensions describe the context, the who, what, where, when. So we'll have tables like store, product, category, vendor, and crucially, a dedicated date dimension.
These are the static-ish details.
Pretty much. Then you have the fact tables. These track the events, the actions. The main one here is sales DexSN, and it needs to be at the line item grain.
Meaning every single item scanned at the checkout gets its own row in this sales XSN table.
Precisely. No grouping yet. Just the raw transactions.
Let's illustrate that. So the sales TXN table becomes quite lean, right? It's got a transaction ID, T6Net, maybe IDs pointing to the store and product.
Yep. Storied, producted. These are foreign keys linking back to the dimension tables. And then the numbers, quantity, QOT, high, the price per unit, unit price, and maybe the total for that line, linear amount. That's it. All the details about what that product actually is, its name, its SKU, its category, its vendor, that lives separately in the product T dimension table.
Linked by that productive.
Exactly. And that product T table itself has foreign keys like categoried and vendorid, linking to other dimension tables.
So if a product switches vendors,
You update one record in the product table instantly. Every past and future sale reflects that change because they all just point to that single updated product record. That's the power of normalization.
Okay, and you mentioned the dim date table. It's not just a list of dates, is it? It needs more detail.
Oh, absolutely. A good date dimension is gold for analysis. You don't just store the date itself. You pre-calculate things like the year Y, the quarter Q, the month M, the day of the week, Dow.
And maybe flags, like Ice Holiday. Definitely has holiday. Because think about the questions the business will ask. Did sales jump because it was a holiday? How do Saturdays compare to Tuesdays? So if you don't pre-calculate those, every single analysis later has to figure it out on the fly.
Which slows everything down. Pre-calculation makes analytics much faster and easier. It gives you the language to talk about time effectively.
Now, this design, this structure, it needs to be documented, right? The requirement mentioned an entity relationship diagram, an ERD, using Mermaid specifically.
Yeah, using something like Mermaid, which is definition as code, is becoming standard practice.
What is that?
Because it means the diagram itself, the blueprint, is just text. You can check it into version control, track changes, regenerate it automatically. It makes the documentation part of the reproducible engineering process.
Okay, so you define the ERD in Mermaid text.
And then you translate that directly into the SQL data definition language, the DDL for Postgres. This is the actual code that creates the tables.
And it has to include all the rules.
All the rules. Primary keys, foreign keys to enforce those links between tables, not NLL constraints where data absolutely must exist, and indexing to make lookups efficient. It's like writing the constitution for your data, right? Setting the ground rules.
Right.
So constitution written, now comes the hard part. Getting the actual data from those messy spreadsheets into this clean structure, ETL, the extract, transform, load phase. And the work actually starts before you even touch the database. It starts with reading those raw CSVs.
How so?
The plan emphasizes reading them into pandas, which is a common data tool, but doing it with explicit data types, D types, and using the parsedates function properly.
Why the emphasis on explicit?
To prevent type drift. You mentioned those columns with mixed numbers and text. If you let the system guess the data type,
It might guess wrong.
it often guesses wrong. I've seen cases where a single badly formatted date made a whole chunk of sales data unusable because the parser just gave up or misinterpreted it completely. Like seeing sales from January 1st, 1900.
Ouch. Okay, so explicit types are crucial for reliable reading.
Critical. Then the T in ETL, the transform step, involves cleaning that data, making types consistent, handling weird values, and figuring out the correct load order.
Load order.
Yeah, you can't load the sales specs and data, which relies on produced and stored, until the product and store tables actually exist and are populated, right? You have to respect the dependencies defined by your foreign keys.
Makes sense. Load the dimensions first, then the facts that reference them.
Exactly. And the whole process, end to end, needs to be idempotent.
Idempotent. That means you can run it again and again, and it won't mess things up.
Precisely. If you run the ETL pipeline a second time with the same input files, the database state should be identical to after the first successful run. It shouldn't create duplicate records or errors.
Why is that so important?
It builds trust and reliability. The data team shouldn't be afraid to run the update process. If something hiccups halfway through, you fix the issue and just rerun it, knowing it will pick up correctly, or simply do nothing if the data's already there. It's a hallmark of professional data engineering.
Okay, so the pipeline runs, data should be loaded. What's next? We trust it.
Absolutely not. Next come the sanity checks. Verification is non-negotiable.
What kind of checks? Basic but vital stuff. Do the row counts in the database tables look reasonable compared to the source files? More importantly, does referential integrity hold? Meaning, are there any sales transactions pointing to a produced cocket that doesn't actually exist in the product's ET table?
Exactly. Those are called orphaned foreign key rows. We need to find them. We also need robust checks for duplicates that might have slipped through. The acceptance criteria are pretty strict here. Get at least 95% of rows loaded, and referential integrity must be perfect. No orphans allowed. Passing those checks is basically the green light. It's the go-ahead, because the data is now structured, it's validated, it's trustworthy. Only then can we finally shift from cleanup mode to actually generating insights. Which brings us to the baseline modeling.
Right, the final piece of challenge year one. The goal here is practical, isn't it? Predict daily sales for each store.
Yeah, something simple but immediately useful, especially with new stores opening. You want a basic forecast to start planning against. We'd use straightforward regression models.
And how do we know if the model's any good?
We measure its error, of course,
Right.
using standard metrics like MAE, mean absolute error, or MAP, mean absolute percentage error.
But just getting an error number isn't enough, is it?
No way. The crucial part is comparing our model's performance against a really simple naive baseline,
Like what?
like predicting that tomorrow's sales will be exactly the same as today's sales, or maybe predicting they'll be the same as the average for that day of the week.
Ah, so if your fancy new model can't even beat that simple prediction.
Then it's not actually adding any value to the business, is it? You have to demonstrate measurable uplift over the simplest possible approach.
Got it. And this whole process, from sketching the ERD to evaluating the model, needs to be documented.
Thoroughly. An executive summary, a presentation detailing the pipeline ingest, normalize, analyze, model, and the key findings.
Now, we should also touch on the role AI played here. It was mentioned in the requirements under AI literacy.
Yeah, it's interesting. AI tools like LLMs were used, but more as accelerators or proposal generators.
So the AI might draft an initial ERD.
Exactly. It could propose a few different schema options based on the input files. The human engineer's job was then to evaluate those proposals, compare them to their own design, and ultimately make the final call,
So the AI gives you a starting point, maybe draft some initial SQL code or a data dictionary.
which can save a lot of time. But the human has to be the editor, the architect. The AI might miss subtle things based on business context.
Like what?
Well, maybe the AI sees a linear amount column and assumes it's always filled. But the human engineer, knowing the messy source data, realizes it was often blank. So the human adds the explicit NUL constraint in the DDL and plans for how to handle those missing values, something the AI likely missed just looking at the structure.
So the human adds the real-world context and enforces the critical business rules.
Mm-hmm.
And getting this foundation right in Challenge O1 is, well, foundational for everything else.
Absolutely. You can see it if you look ahead at the subsequent challenges mentioned in the sources. Challenge A2 is all about deep data quality fixes, dealing with those tricky category drifts that normalization alone couldn't fix, or handling time zone issues.
You can't do that effectively if your basic table structure is still shaky.
Nope.
And once the data is truly clean after Challenge O2, then Challenge O3 can focus on the interesting stuff. Trends, forecasting, factoring in holidays, seasonality, maybe even weather impacts. And Challenge O4 goes even further.
Yeah, that one gets into customer behavior, modeling the impact of membership programs, calculating the ROI on specific promotions, really valuable stuff.
But none of that advanced analysis. The quality checks, the forecasting, the ROI modeling, none of it works reliably without the stable 3NF foundation built right here in Challenge O1.
It all rests on this first step.
So the takeaway for you, the listener, seems crystal clear. Modern tools, even sophisticated AI, can speed things up, they can draft things for you, but they don't remove the need for careful, meticulous, foundational data engineering.
You still have to understand the principles, nail the schema design, enforce the data integrity rules, and build that reliable, idempotent pipeline. That's the bedrock. We've traced that journey today, taking the Excel spaghetti, normalizing it into clean dimension and fact tables in Postgres, building the ETL to load it reliably, and then running that first crucial baseline model, from chaos to a structured, usable foundation.
Which leads us to a final thought. We started by fixing a mess created by, well, human processes leading to messy data. The solution involved using AI to help draft a better structure.
But the human engineer had the final say, editing the DDL, setting the constraints, taking responsibility for the architecture. So here's the question to ponder. As AI gets better at drafting these systems, where does its speed end and our ultimate accountability begin? If that AI-assisted pipeline fails silently because of one edge case you didn't catch in the design review, who's responsible when the business makes a bad decision based on that flawed data? Someone still have to sign off on the final blueprint. The accountability, I think, still rests firmly with the human architect.
Something to think about on your next data project. Thanks for diving deep with us today.